So, welcome to everyone. My name is Vijayendra Bhamidipati. You can call me Vijay. I'm from eBay. And I'm presenting this work that I've done with my colleagues Michael Chan and Arpit Jain. Today I'm going to talk about instrumentation, resource allocation, monitoring, a bit of billing, as well as security for smart contracts and blockchain frameworks. So, let's get started. The agenda for today is split into the following. First, we'll very briefly visit visibility and metrics. What do they mean? Next, we'll look at instrumentation of systems and blockchain frameworks. After that, we'll talk a bit about billing for smart contracts. And then we'll visit resource allocation, followed by monitoring and alerting, and finally, security. So the first item on our agenda, visibility and metrics. So what's visibility, right? Think of it as an X-ray or MRI or whatever you call it. It's the ability to dissect your system and analyze it completely, at least have what it takes to analyze. So what are some examples of visibility in a blockchain, rather in any context, not just blockchain? Things like components that make up your system, both the core components, your perimeter components, and so on. How about data flows, control flows? System policies, right? What are the policies that you configured on your system? It could be anything. And then behavioral patterns. What is the behavior of your entire ecosystem? So these are all examples of, general examples of what, examples of visibility. Now, what's visibility in a blockchain ecosystem? Let's look at some examples. The first could be what validators are running in your entire blockchain network. If you're running a permission blockchain, what permission views have been configured? What smart contracts have been deployed on your system, right? You would like to have very good visibility into that. How about tokens? If your blockchain framework actually supports the creation of tokens, right? You'd like to know that. If you have created a token, you'd still like to have some visibility into it. Next, what consensus algorithms are being used in your network? What's the current state, scale, and throughput of your deployment? So these two are kind of related. You can have a large scale of operations but low throughput, like Bitcoin, or you could have large scale and large throughput. It really depends on the consensus. So these are just some of the examples. Now that we know what visibility is, let's look at metrics. Now what's metrics, right? It's really a numerical state of any parameter that belongs to visibility. So there are certain classes of metrics. So let's look at health metrics, right? What are these? Basically anything to do with the health of your ecosystem. So things like, is any component up or down? Is it deadlocked? Is it blocked? Are there any deviations from expected states? And so on. Next class of metrics would be resource utilization metrics. What's your CPU utilization, network utilization, right? I/O, disk, basically, and things like that, memory. So here, in the blockchain setting, you'd like to know the resource utilization that's being, consumed by your blockchain framework as well as your smart contracts in a granular manner. How about the third class? This is basically infrastructural metrics. In a blockchain setting, this could mean things like, if you're using proof of work, right? What's the hash rate of your network? What's the number of blocks getting mined, right? What's the block read time? What's the block write time? What's the performance of your consensus algorithm looking like? So, these are the things that you need to think of. This is a separate class of metrics. Finally, we've got the business logic class. This essentially boils down to your smart contracts, right? And there you have two broad classes within them. The first is basically the latency, the overall latency or more granular latencies of the functions in your smart contracts. And specifically, if they're making external calls using something like Oracleize, which is a really popular package, you would want to know the performance of those calls as well, because that's in a way external to your own system. So in this context, let's also make a small note on debuggability. Now, debuggability is actually closely tied traditionally to visibility and metrics. This includes having the ability to have debug builds, having the ability to do live and offline debugging using those builds, having robust test frameworks, and also logging. Logging is actually very underrated. It's very powerful. You can get a lot of insights using logging through log analytics. So you need to also prepare to have a very powerful and robust framework for that. So with this background, let's move into the next item on our agenda, which is instrumenting systems and blockchain frameworks. So what's instrumentation? Any framework that lets you basically create metrics, emit those metrics, collect those metrics, and then process those metrics, do something with them, right? Analyze, for example. That is categorizable as instrumentation. It's an overall umbrella term. What are the traditional resource utilization measurement or profiling techniques that we've all used? They're broadly in two classes again. One would be language-specific profiling tools. So this includes your language profilers like Golang profiler or Python profiling and so on. So these kind of depend on the language for support, but they're very popular and they're very useful. Next, you got system-level profiling. These are all your htop, ctop, sar, vmstat, iostat, and all these commands, right, which admins use a lot and we're very comfortable with. So they're pretty useful, but they have certain disadvantages. What are the main disadvantages? The first thing is that they're not granular enough, right? What does this mean? This means that you can get those metrics, but at the max at a process ID level or at a thread ID level. You can't go beyond that. Now, that said, that is basically for your system level metrics. How about your profiling? The language-based profiling that I mentioned. Now, that's more granular, agreed. However, it should be planned ahead of time. Today, the way it works is that you actually have to edit that code. You'll have to bring it up in a test or dev environment, and then measure it, and come to a conclusion saying, OK, this is OK. We cannot scale it fully, but we are OK with it, and you push it to production, right? It's not really ideal if you want to push something like that to production. And in the case of blockchain, smart contracts are immutable, right? Once you push that in, it's there. It's baked in. You don't want that. So these are the disadvantages of traditional profiling. Before we continue, I'd like to make a note on Hyperledger Caliper. This is a new project that's been incubated. Incidentally, it got incubated into the Hyperledger umbrella around a couple of weeks after we submitted this for the talk as a submission. So while Caliper is really powerful, and we like it a lot, we are yet to go into much depth into it, but we do note that it also requires code modification. So you still have to modify the code that you write for instrumentation. So is there an alternative? Yes, and it's called eBPF, Extended Berkeley Packet Filter. So what is eBPF? eBPF, many of you may have heard of it. It's actually a very powerful framework that is provided by the Linux kernel. What it does is that it's highly programmable. It has quite a good instruction set that it supports. It basically deploys what we call an eBPF probe inside a very tiny virtual machine, which is really a term to refer to some sandboxed space, if you can call that. It's not exactly sandboxed, but it's very secure. It's highly granular because, as we'll show you in the demo, as I'll show you in the demo next, it's extremely granular. It can be inline in the sense that it is almost always inline, and it does not require you to modify your code. That is the biggest draw of eBPF. Specifically, we are going to be looking at a functionality that was very recently introduced in eBPF called FBT, or function boundary tracing. Now, it's ideal for something like blockchain and smart contracts. Why? Because it's immutable, right? All these are immutable in the blockchain, and you can still go ahead and profile them in production systems. Remember dtrace in Solaris? This is it, right? It's the equivalent in Linux. As one of my colleagues mentioned, QI, he said, this is the way to make Linux great again. So so there are two ways to run eBPF probes today. The first is called Linux Perf. The second is called iOS at BCC. Both of them are open source, very popular. There's a third one called Ply in the works, but it's a bit further from maturity as of now. So the preferred one is iOS at BCC. So I've already mentioned that it brings in visibility at user space function level. I did not mention that, actually. So this is the big deal about eBPF. At user space, at function call level, you can get visibility. The demo will make this clearer. If you couple this with something like call graphing, what is call graphing? In call graphing, you basically do your static code analysis and then build an entire directed graph of all the possible function calls in your packages, among your packages. This is a very powerful feature. If you combine both of these, you can pretty much measure things like latency of functions, specifically function chains in a smart contract, or even in the underlying blockchain infrastructure. And you could look at resource utilization of these functions as well. In our demo, we are going to show you the function latency. So this is an overview of our demo. On this big box, you see Hyperledger Fabric. We are bringing it up in a single node installation using the dev mode, which is very convenient. It has a very nice Docker Compose file. So what we do next is that we've created a very simple smart contract, a chain code, which we call myEcoAsset. All it does is that it echoes an argument that you send to it. That's it. And we'll keep invoking it. While we are invoking it, in parallel, we are going to start an eBPF probe to trace a specific function called the invoke function. We could trace any function chain, but in our demo, you'll see that we are tracing invoke. Now, after that runs, we'll bring in a stats emitter. In typical production, you would actually have the stats emitter running continuously. For the sake of the demo, we've kind of split it to make it easier and for people to follow. That writes to an index on an Elasticsearch container that we bring up in the same box. And that renders a couple of dashboards that you can see on Kibana, which is again on the same box. So this is a layout. It's in Tmux, so that's the reason I created this. Basically, you got, I hope the font is okay. But you got Hyperledger Fabric and Elasticsearch and Kibana running on the left. What we'll do first is we'll look at the chain code file itself, the smart contract. Then we'll build it and run it. And then we'll start the eBPF tracer. And then we'll start invoking the chain code, like around 500 times in our case. After it runs, we'll start a metrics emitter that'll collect these metrics and emit them to Elasticsearch and Kibana. So let's get started with the demo. So I sincerely hope everyone can see the contents of the demo. Oh, sorry. So, is everyone able to see it better now? OK. Should have made the font bigger. Anyway, this is the myEcoAsset. This is basically in Golang. We chose Golang to write the chain code. And you see that it has an invoke function and an init function. These are standard Fabric, Hyperledger Fabric calls, right? And this is the echo function, which is being called by the invoke function. And what it does is that the invoke function basically sees, hey, if an argument is echo and it's getting an argument, if the command is echo, it'll just call into the echo function. That's it. It's a very simple smart contract. So next step, like I mentioned, we've actually already built it and executed it. I'm just showing you that it was already done. As you can see, it's Docker exec into the chain code container, which is a helper container that Fabric provides. And we've done a Go build with GC flags over there. And we have already brought it up, and we pointed it to the peer on 7052. Now here, I'm opening the script, which actually launches an eBPF probe. And it's called funclatency.py. This is a standard BCC IOvisor eBPF wrapper that has been written. We did this on purpose to keep it all open and simple for you to follow. What we're doing here is that if you see that specific line, it says myEcoAsset :main with a star, myEcoAsset star, and a function as a parameter. What we're doing here is we are passing a regular expression to eBPF, and we are asking it to start profiling it. And this is really powerful. This is extremely powerful. So now what I'm doing is that I'm firing off this eBPF probe, and it's active in this window. Now that it's active, what do? You go ahead and start invoking the chain code many times. So in that for loop, it's just for I in sequence 500, and we're saying a PR chain code invoke myEcoAsset with an argument echo and arg1, right, with two arguments. The first one is parsed by our chain code as a command, and the second is taken as the argument. Now that's running there. Now you may be wondering, why is the smart contract actually running constantly? What does it do? In the background, the smart contract establishes, when you start it up, a gRPC session socket with the peer. which is there. And every time you invoke the smart contract or chain code, a transaction is actually recorded in the blockchain itself. So the peer and the orderer are making these records. So you actually know that it's being invoked. Now, this is a previous run of this demo. We have 2 dashboards already populated. The function on the second is the echo, and on the right it was invoke. But we'll get back there. So now what we're doing is that we are profiling invoke, because here, when I invoked it, I said, wow, the font is like, I'm sorry about that. But I basically asked it to trace the invoke function specifically. So the invoke internally calls echo in this case. Now let it run for a while. In that window, I'm opening the metrics emitter.sh. It's a simple shell script. The metrics emitter, before that, I did a Docker PS just to confirm that, hey, everything runs as I'm claiming it. There's the chain code, CLI, peer, and orderer, which are all Fabric containers. You also saw an Elasticsearch and Kibana container there. So let's, I'm now going to execute the send metrics.sh, but before that, I'll just kill the eBPF probe. Now, this doesn't have to be done. You can still have it running. I just killed it for simplicity and to show what the output looks like. This eBPF probe, in this case, builds a histogram of the latencies of this invoke function. And you can see that there are multiple buckets of those. And when we look at the graph that gets rendered, it'll become clearer. So the send metrics, what does it do? It actually starts reading this. It takes a bucket, randomizes the value within the bucket, and then emits them. Now, in real production, you don't have to randomize or do any such thing. We are doing it for the purposes of the demo. Now, what you see there is that JSON that's being spat out. That's actually each is a record. Each is a metrics record. And if you look at the Kibana dashboard, you see that it's periodically increasing. The log counts are increasing. Now that that is done, we're just refreshing it to show you how the emission's working. Then we go to the dashboard, and we'll refresh these 2 dashboards that we saw earlier. Earlier, they already had some values, right? So in the last 1 hour, let's just go ahead and refresh them. Now, what you see is that we did not trace echo, so that stays there, but new values for invoke are started to get traced. And you see that the latency is around, but it started off, the last value was at 70,000 nanoseconds, which is 70 milliseconds, and it came to around 35 milliseconds in the next run, right? Imagine this. You have actually traced a function chain, main call something, call something, call something, right? That's a call graph entry. You trace that without any modification to your code. This is an extremely powerful thing, as we'll see later. This concludes our demo, so let's get back to our presentation. Excuse me. So now we've seen eBPF, but obviously there are going to be drawbacks to anything. What are the drawbacks of eBPF? These are more like current day drawbacks. The first thing is it's available only on Linux 4.4 kernels and beyond. So any older kernel or non-Linux, you don't really have this functionality. So what do you do? An alternative is to build this functionality into your virtual machine itself that runs your smart contracts. Now, Fabric doesn't do that, but Ethereum VM exists, and you can actually pull something like that. You can put such kind of functionality into those VMs, right? You could do that. Next, obviously, this will require blockchain support. The framework has to do it. But if you want even more tracing, you'll have to build such functionality into the blockchain framework itself so you can trace the blockchain framework's performance itself. So ideally, you would just rather go with eBPF, wouldn't you? There's another thing about scalability. Now today, for Golang, for example, you can attach around 1,000 eBPF probes at any given time. This is being worked upon. It will improve with time. And probably at this stage, we'll not need more than that, but I'm always wrong when I make such statements. So scalability is something that we need to think of. So now we've looked at visibility and metrics. We've looked at how to get those metrics, right, in a non-invasive way. What do you do with that? One application is billing. So let's look at billing. How are you going to bill smart contracts? Billing for blockchain ecosystems can be of 2 types, based on what kind of blockchain you are deploying. The first is a public blockchain. How does billing in a public blockchain work today? Typically, it works like this. I have a transaction. I would like to get the transaction written to a block in the blockchain, but when? Either in the next few minutes or in the next X number of blocks. They both are almost interchangeable. So the thing is, say, take Ethereum, for example. You set a gas price. If you set a very high gas price, it's more probable that your transaction will make it to the very next block, being returned to the blockchain. It's possible. It's not a given. So the point here is that variability is OK in public blockchains as of today. That may change, but as of today, it's typically OK. But if you look at a permissioned or private blockchain ecosystem, is variability OK? Not really, because you will really have to think about quality of service and also about your OpEx. You cannot really afford delays. In most enterprise deployments, you'd like to completely have no delays, right? So these are classes of billing. So now that we've identified that, hey, these two are different, what could be the drivers that could drive something like billing in enterprise ecosystems? There are many examples, but essentially the point is that it has to be multivariate. It can't be too simple. So let's look at some of the examples. Specific function chain latency, which we just measured. That's an example. Partnership service charges. What does this mean? You got a permission blockchain with multiple partners, right? You may want to have some preferred partners and some not so preferred partners, and you may want to charge them in a differential way, right? The third thing is IP-valued smart contract services. So you got some IP that you're coding into a smart contract. You would obviously want to do some billing based on that. How about demand-based contract service or pricing? Say tomorrow you come out with a competition, blockchain-based competition or competitor to Uber or Lyft, right? And you want to do something like surge pricing, right? You need to be able to take that into account for your billing. How about resource utilization-based pricing? This is classic. You don't want to lose the capability of billing based on resource utilization. Then the last thing is sublicensing. How about sublicensing? You have a partner, you actually licensed some IP or something to the partner, but the partner goes ahead and sublicenses it. You need to be able to track that. Otherwise, you'll be losing money, right? You'll be losing out on royalties. So these are all examples of how billing should be built in a blockchain ecosystem, and blockchain frameworks in general can help a lot in building such billing frameworks in a very trackable way. So next on our agenda, resource allocation. So to do something like billing, you can bill, but if your customer says or your partner says, I never asked you for this, right? What do? You have to have some way of allocating, of capping your resources or giving a lot more resources. So typically when we talk about resource allocation, again, there are two parts to this. One are the engines that dictate the resource allocation policies. You need a policy engine of some sort. The second thing is your data plane or something that enforces this resource allocation, right? That's basically your allocation engine or allocation plane, sorry. Excuse me. So let's take a look at the resource allocation plane, right? How would you, so first we are looking at the data plane. So how would you implement such an allocation plane? A very low-hanging fruit is containerization, right? It's readily available as a Linux construct. It also has good orchestration support, like Kubernetes. It allows for resource requests as well as limits. But it's not, again, that granular. It can be granular if you're going to run only one smart contract with exactly one process, basically, in each container, right? But that may not always fit enterprise requirements. Too many times we've seen that we will have to have a lot of helper containers in a single pod, and they start taking up logs, resources. A very good example is something like Firebase, logging, basically. It can become a system hog very quickly. So what do? You can have multiple of these blockchain logical constructs in a single namespace, but you can't really allocate resources between them, right? It doesn't let you do that. So what we propose at eBay is using something called blockchain-aware native scheduling. It's not really using, or more it's like building. We propose to build this. Let's look at what blockchain-aware native scheduling means. But before we look at that, when we talk about resource allocation, let's look at the constructs for the blockchain ecosystem. So you got business logic, specific smart contracts. You got quality of service, which essentially are reflected in latency requirements. But you also have classes of service. What does this mean? Examples of this are IoT, DRM, and financial transactions. Just take a look at these. These are all very different classes of service. They all have very different environments and ecosystems and very different requirements, right? So you need to be able to differentiate between these classes of service when it comes to how you're going to allocate resources. This is an important point. Then again, there are the environments. Where are your customers coming from? Where are your requests coming from? Are they coming from mobile or desktop or native apps on mobile? And so on and so forth. Now, let's look at blockchain-aware native scheduling. What this really proposes is, build smart contract awareness into the kernel itself as kernel modules and/or constructs, right? Like Linux containers did this with namespaces. It built the building blocks that made it possible to build containers, right? Linux did that. Similarly, think on similar terms when it comes to the blockchain. You build things like consensus algorithms as protocol suites into the kernel itself, and you'll have full native support on every system out there. Think about embedded systems. They'll have lean implementations of these. Think about security, right? There are already products coming out with secure wallets on the blockchain, but this goes way beyond that. This is part of a paradigm. Now that we've spoken about the data plane, let's look at the control plane, resource allocation engine, right? It's really the control plane. It can be, again, of two types. You can have a basic allocation engine with just simple policies, and you can say, hey, just, I'm going to write up these policies and just, send them off to the allocation engine to actually do its job, right? To the data plane. However, what we think is that this should not be so simple. Rather, it won't be enough if it's so simple. It should be more advanced. And specifically, we should leverage ML or statistical methods to identify patterns of usage. You need to have a way to first collect, which we have, all the metrics, and then identify the patterns of usage and let it drive your resource allocation. So next on our agenda is monitoring and alerting. This I'll kind of touch quickly. You've already seen this in our demo. We use Elasticsearch and Kibana. There are many suites already in use and very popular in enterprise environments for this. You got Prometheus. Instead of the simple stats emitter that we had, you could actually have those emitted by a Prometheus handler to a Prometheus or federated Prometheus environment. You could have StatsD and FileBeat and Logstash. FileBeat and Logstash are very popular for log analysis, right? For log processing, and it's an entire log pipeline. Then, of course, we have Elasticsearch and Kibana, which we just showed you what it can do. Elasticsearch can scale quite a bit, and this can help analysis of your enterprise blockchain ecosystem much better. There's also Grafana, which I haven't listed here. It's a very popular rendering tool, graphical rendering tool. So finally on our agenda, we look at security. So what about security? Again, there are two parts. On the same lines as resource allocation, you have the engines that can dictate security policies. You can have planes that realize these security policies. So let's look at them. Here's the thing. After looking at our eBPF demo, we realized that if you can trace it or track it, you can block it. So we propose using two approaches for this. The first we call function-based access control, or FBAC, and the second is what we call data-based access control, or DBAC. Let's take a deeper look into each of these. FBAC, what does this do? It blocks or allows invocations of specific function chains. Just think about it. User space functions in the blockchain framework, as well as your smart contracts. There's no distinction, really. If you want to make a distinction, you can build that into your logic. But any function chain in any smart contract or in the blockchain infrastructure itself, you can block. Let that sink in. You can create whitelists and blacklists of such FBAC policies, right? That you can bake into the blockchain itself. So you use the blockchain to secure the secure data policies that will secure the blockchain, right? That's what it really does. It uses its own power to secure itself. But what is crucial in this idea is that really, if you think about it, it is an extremely scalable way of implementing permissioned blockchains. What is a permission blockchain? What is a permission view? You really, if you think about it, it really boils down to a combination of FBAC and DBAC. That's what it is, and that is what this can let you do. So now DBAC, database access control. Same here. You block or allow invocations of specific function chains, but then you go beyond just the function names or the function chains and start looking at the parameters that those functions carry. This can be extremely powerful too, right? Of course, with things like encrypted data, you may not be able to do much today. But if you were to do this in FBAC, then that opens a door for you to do something like that securely, even for encrypted data. Now, you can also block or allow reads or even writes of specific sets of data. You can have whitelists or blacklists of these DBAC policies that are baked into the blockchain itself, obviously, right? So these are two new paradigms that we propose. So how would you actually implement it, FBAC or DBAC? There are again two approaches. One, we've already showed you eBPF. Today, eBPF is really programmable. If you were to look at the underlying implementation of how eBPF does this, you can take a look at tools like SecComp, AppArmor. They have been around for a while, right? They use eBPF internally. But they use what is called a landlock feature of eBPF, where you can either allow or deny a landlock for a specific function chain. But they do it at the syscall level. Why? Because they're more, they're more common, and somehow no one has actually done it for. As far as I know, no one has done it for user space functions yet. But it should be very simple to implement because we already have function boundary tracing, which is able to track the very entry and the exit of the functions. So it's just going to be, a pluggability problem that we're going to be solving. If you don't have eBPF, what do you do about that, right? You don't have eBPF support. Then it's fine. You can still build an intercept in the VM that runs your smart contracts, or natively into the blockchain framework that runs your smart contracts, right? So this is my team, the blockchain team at eBay. It's Michael, myself, Arpit, Brian, Ashok, and Derek. There are a couple of other teams as well. Connie is here as well. Hi, Connie. Feel free to reach out to us with any questions that you may have, and we will be happy to respond as best as we are allowed to. A note of thanks to Venkatesh, Brian, as well as QI. And here are some references that we think are going to be pretty interesting for the audience. You can go through them. We're open to Q&A. Any questions? Yes. I think there's a mic somewhere here. There's one there. It doesn't work, sorry. Now it works.
I was saying, can you just show the page before to see the...
Oh yeah, sure. I think these slides will be made available. Yeah, so, they are available, yeah, I uploaded them. Yeah, so, yep. Yes, please. Yeah, I'll just pass the mic myself. Let me do that.
Hello. What will be your approach to monitor a blockchain network composed of multi-organization and multiple nodes? Mm-hmm. How will you recollect and use those metrics?
Yeah. That's a great question. So basically, the question was, how do you do this across multiple nodes, right? It's pretty simple. You have agents or containers. There are many ways of doing this, but essentially you need some sort of an entity on each node that can collect the metrics for you. In case of public blockchains, this may have to be absolutely baked into the blockchain itself, and somehow every participant has to allow for that to be run. It needs some level of privilege, obviously. But if you build it into the blockchain framework itself, then it's fine. You can already get it natively, right? In case of permissioned or private blockchains, it's a lot easier. Why am I using two mics? Sorry. It can actually be much simpler. It can be much simpler in the case of permission blockchains, because you have a certain amount of vetting in private or permission blockchains. You know that you're going with trusted partners, and so you can say that, look, you are anyway participating in this framework, have these agents, have this code also run. They can turn it on and off if they want to, but for something like dynamic resource allocation, or even many higher layers are possible to build on top of this, like superbly. And for all those, you may never want to turn them off, right? The best thing about something like eBPF is how efficient it is. It's almost negligible CPU usage because it's inline, and there's usually no context switch of any sort because the VM actually runs in the kernel itself, and it's on the way it's on the way to and fro. It's inline. So typically, to give you an example, if you were to deploy an eBPF probe in the network stack, the effect on the CPU for like a 10 gig network would still be like 0.5%, which is negligible, absolutely negligible. Maximum is 1%. So this is what makes eBPF like really powerful and attractive.
I think at one point you had said there are some billing tools out there that are available. Do you have any recommendations to look at?
No, I don't.
Okay.
Due to two reasons. Frankly, I'm not a billing expert, but I don't look at it from a product perspective. While I have mentioned some with respect to things like Elasticsearch and Kibana, because they're very much open source. Billing is not so open source, as far as I know. Yeah, that's a problem. And a framework like this can actually make billing maybe open source. It can nudge it towards that, because this is an open source fundamental framework that exists already, right? So you could probably build that in an open source way. This could encourage that. Any other questions? How are we doing on time? I guess I finished it too fast. Yes.
So I noticed here that this is a bunch of tutorials. I'm wondering, are you thinking about packing all of your knowledge into some kind of monitoring framework for Hyperledger, like mostly this BPF stuff?
So are we planning to contribute?
Yes. Are you planning to create it into a ready final framework with all of this inside?
Sure. We are actually, I can't make any promises, unfortunately. But yes, we'd be happy to be able to contribute to the world back. But at this stage, I really can't say anything about it. Yeah, sorry about that. But and we've deliberately made this talk as open as possible, as fundamental as possible, to showcase the possibilities that, and the approaches to which, the approaches that can be used towards building such ecosystems. Any other questions? Well, thank you. You've been a wonderful audience, and thank you very much.